So we have today, I know what I forgot. Seminar number
7 or 6.
7.
Yay.
And I will open this already online, so we're just going to go through the Moodle page. Oops, no, that was number 6. Number 7. It's basically on HLS, but to pass the seminar, actually, to be fair, you do not need to do HLS. But basically, the task is to make a HLS project development and deploy that into your FPGA, make such, in this sense, essentially your own like firmware. Essentially, what you will then have to do is go through different stages. I will explain you what the idea is of the project, and we can then discuss, and when you drop me a message or whatever, what the project will be. And you just need some points out of it because you need 70%, but unless you did all the bonus points in the previous assignments, you do not get the 70% yet. So so basically, this is a concluding assignment where you should do all the stages of it, and that would allow you, and that would allow us to see that you can do an entire FPGA design flow from an HLS idea to the implementation and looking how the design performs. So this would include, you're expected to come up with your own small project, very tiny, can be a few lines in HLS, very short. I will show how HLS works in a bit. But just very short, a few lines of code in there, a small project which use all the different tools introduced in the course, plus developing your own design. So, which means you have to do a design concept development, right? Coming up with an idea, and put that through the FPGA development workflow stages, HLS development, IP core utilization, on-chip communication, simulation, implementation, placement, and routing, and the according analysis for each of the stages. For each of the topic, you will have 1 point, so all the course topics are covered in the project. Additionally, points will be given for design, implementation, and report quality. So basically, the goal is in FPGA is always very important to be consistent with your coding style, with your comments, with your documentation of that. So that is encouraged because you will get a point for it. And no matter how far you get, you can always make a documentation. If you fail along the stage, and you have documented each of the points and the according failures, that is also sufficient. There's a lot of cleanliness and documentation completeness important because FPGA design or chip designs are about cleanliness and well-structured designs. We have 1 task with this, and each of the following stages will give you, no, I'm counting. Basically for the stages, which is in different words phrased. So you're not expected to make any complex project. You are expected to submit a full minimum required code basis. So I do not want that you zip up the entire project with all the cache files and everything. I want that you take those files out, which I would need for design entry. You can also use the ticker script function, which I've used myself, and send that with the according files. Whatever you do is up to you. If you can load it from an empty project with only those files, then it's going to work for me as well. So that would actually be the easiest because then I have 1 click and I see that the project works or not. And yeah, so that you do each of the workflow steps. And if you're not sure if your project is too big or too small, you can just reach out to us. That's the goal, so that we can discuss a bit how big a project would be or how complex things would be. So in each of the points will be given to explain your design, supported by visualizations. So I do not want a pure text. I want some kind of visualization. If there's a block diagram, a flow diagram, state diagram, whatever, it doesn't matter. Just something where I can see this is the idea and that's how it's supposed to go. Report briefly on each of your development workflow stages. So if you go through the stage, how they went, what problems you encountered, and then again, these are already 2 simple points, and then everything on top will be needed, whatever you need to do, or educational for you. Utilize Vitis HLS to create at least a small IP core, and I will show you how simple that is. So that is something which is also kind of given. Utilize at least 1 IP core in your design. again, you will have created just one. If you're nice to me, you will use another IP core just for the fun of it. But I don't mind if it's just the one which you just created. For example, you can do a soft core with connecting with your HLS and then make an Ethernet interface, whatever you want. Doesn't matter. Whatever ideas you have, would utilize on-chip communication in your design. I will also show you an example so you see how easy that is as well as if you want to with HLS. And then describe a simulation approach, expected results. Look at the last lecture. That might help you a lot to find a simulation approach. It's very simple. And then provide a log report as well as a waveform diagram and outline challenges or problems which you needed to debug a bit. Describe what constraints you had to come up, any challenges encountered with doing roost, placement, routing. I do not expect major challenges because you will have a fairly small design because it's not supposed to be forever long. Of course, you can push here also the limits of your design, so you can just put, if you use a FIFO, just crank it up to the maximum FIFO size, and then you will use a lot of your logic and a lot of your memories to alone have a big FIFO. And then the last 2 points are provide a design analysis, which basically on resource, power, and timing on the different workflow stages, at least synthesis and implementation, and then introduce your file hierarchy, optimization scripts, and so on, and README. So in a good project, it belongs to README, so you know what is going on and what kind of workflow you use and what tools you use. And then in the end, overall, this additional point is reward for a project follows consistent coding styling and commenting, except for auto-generated files. So if you do HLS and you comment your C code, I do not expect you to go into the VHDL generated files and comment those. That would be a bit much to do maybe. So that would be this part. So that would be the assignment. Everything which I said is literally written in this, so I will not go more into detail unless there's questions right now on that. So any project idea, whatever you have is free. So this really allow you to explore.
I have custom board. Can I use that?
It doesn't matter as long as you tell me which device it is.
7000.
Yes. I mean, this you can try this.
I want to practice Ethernet stuff, so I want to try it.
Yes. Be aware that whatever this course does do practical FPGA design, we don't go into any drivers or anything, which is actually the more difficult part of this, to be honest.
No, I mean the drivers must probably already exist somewhere.
If they don't, yeah.
IP cores, but
Yeah.
basically
the usage of IP.
Yeah. So searching still. It's
Yeah. So for your search, you will probably want to use Vitus HLS 2024, which is not Vitus. Be aware of the difference, although I think these days it opens the same software. I've not checked it in detail. So, and this is now, and now I'm opening it twice actually, never mind. Here. So this is basically what you get. It looks awkwardly familiar probably to VS Code. That has changed, I think, since last or this year. So it's the first version like this. And if you know how to use VS Code, then you're going to be fine. Overall, also things like git lens and whatever is introduced. So if you want to use those, it's directly there, and I would recommend to use it just for coding structure, essentially. Here, there's also a lot of, directly included, there are a lot of examples. So if you do not know how to do anything, there's good examples which tell you how to, for example, let's go into HLS examples, interface, here, memory, whatever, or streaming. Then it will directly go into it. It will tell me how to do different AXI examples. And I can create in the project accordingly. And basically, I go here into whatever it is, here, create project, and I will define the path for this, and then I create next. I have done this already, but I've not opened it right now. So let's.
You have to create a new project. You cannot preview this stuff.
Yes, you can't, but it's also like taking a few seconds to create. So I have a workspace in here, and you will see how it looks when you have multiple like this. Then it will open it, generate it very quickly, download it if needed. And there's a lot of examples. Don't hesitate to go into it. Will be quite useful for you. All of these projects are always based on some JSON files where they download paths, so on and so on. So you can download it, and when this is done.
5 minutes later.
You can maybe open another instance.
I will just close this instance, not gonna lie. 24, let's go from again. open workspace. Let's do it right this way then. So here we are. Yes. So basically, you see here I've already loaded different projects. That's why I wanted to go into this workspace specifically and did not want to load others double. You see here that on the left top you have your Vitus components or whatever your folder. It's like, so your Explorer. You have all your folder paths in there and all the settings and everything it includes. It's a bit, you see already it's a bit prepped here and a bit adapted. It's not just files. Then down here you have your so-called HLS flow. It's a bit different, but you will see similarities, let's call it, to what you have otherwise ongoing. And so there's a simulation, a C simulation, which will essentially code your C code as if it would be FPGA code. Like it already does that. C synthesis, and then you do the low-level co-simulation, so between your C level and your VHDL with outcomes, and we'll compare this to each other. This co-simulation, as introduced in the lecture, then you can package it and implement it, but you also can just package it and put it into Vivado. That's what I'm going to show you in this demo. There is one using AXI example, and you see that I've already run here some stages when I open this. In the sources, example CPP. Yes, it's a CPP file, but you use a different compiler. That's essentially what HLS is. It's a compiler which converts it, actually, if you want to be precise, into LLVM intermediate representation, and then puts that into VHDL afterwards. So there's a layer in between. I will explain probably on Tuesday some of this stuff because I've worked extensively with it, so you actually see what is possible in the scope of HLS and research activities. And then you see very classic C code. You make just a void example. And then the difference essentially is here those pragmas, and that will define an interface, such as an AXI interface. This one is a normal AXI master, and then you will refer to A and will basically write and read from A accordingly, memory copy functions. That's for you to test out, and then this I will show you, will create an AXI master interface. And in here, there's just an example. This one counts up to 50 and adds each time 100. So I expect a bit more creativity from whatever example you come up with your math or whatever you want to do. Come up with something funny. You can already use this based on this example and then go and do whatever you want. And the rest is a bit C coding. Of course, if you want to, you're welcome to explore whatever pragmas as introduced in the lecture, unrolling, pipelining, and all these kind of things. So you can do that. And then you just run through the different parts. In this example, there's also directly a test bench included. So you have a test bench which actually will trigger the example function and will give you the result simulated back. So if I run a simulation now, I get here down here a log, and it will run the simulation. And in a second, will also give me the result. And of course, I have an error. Wonderful demonstration. C simulation is finished successful. I had some errors. Anyways, but you get the idea. So basically, you have a test bench, and that will give you the result. And if you do some printf, see a success in hardware and simulation results match here, which appears in here in this line. So what I've written seems to be correct as expected. And I probably had here some dependency searches which went wrong, but they did not have a simulation impact. Then you can go through synthesis and so on. I will not do this right now, but I will go into the settings just to show you what you would need to do to get it as an IP core. And I hope I opened the right settings right now here. No, this was not the right setting. You can, packaging. Exactly, so here, I hope this is big enough for everyone. In your settings, you will have an IPXO setting and packaging. And here you can specify which output file format you have. And down here, you can get which level you want to have. If you want to use it for your assignments, I would recommend to put it as an IP catalog, and that will be exported. You just get that IP catalog out, and you load it as IP core into Vivado, and that's what I'm going to show you in a second. And then you get that IP core loaded into Vivado, and you're done. So, but it is set by default to XO, which I actually, to be honest, do not know. And HLS is a topic which itself, HLS from C++, I've not worked with. I've used with the open source front end and getting results then through the back end and out. So I think it's pretty clear. You can also run the implementation, and you might even get directly firmware, which you could put onto a system on chip directly. So, and then you can put that and open up the C project, which runs your processor and communicates immediately with the C code, which is not actual C code, but it's the hardware FPGA C code. So that's the HLS part. So if I do here now IP catalog, I could also specify probably the path somewhere. Output bar for the file generator. Well, you see also directly here git ignores. I will try to have, oh yeah, exactly. So I already made an, oh yeah, probably I should show this because I had some issues with this. Let's make a quick, no, IPs. And then I should allow me to, no, it doesn't. It wants a file name, obviously it does. If I would know what the file. Okay, so this also worked without. I will show you the workaround for this in a second. So basically I can run the packaging, and now I need to improvise properly, where hopefully I will create and run and package this IP core. And exactly, that's what I used. I used the path IP created in here, which means I will just go into my VS Code or whatever, and go through this. No, into HLS test, and then Axie master, and then whatever path down here, and then you can copy it over. I have, of course, done that already before, so I will not do this now again. And then I have IPs, I copied it then over into HLS cores, and then you have a zip file, which I basically unzipped, and when you then go into your Vivado, and you start a new project, whatever it is, I will just quickly click through here, FPGA Design, assignment 7, create subdirectory. I go here through here. Well, I do not need to add anything right now. I will just take whatever I will find. I will take the basis board. We'll select this. Go through here. All doesn't matter. I just want to have a new project to show you this. And you would have, of course, added your other files or whatever IP cores which you would like to have used. And then either, as usual, I can add my own IP core here to IP catalog and go through. I will show you actually another way so you don't have to use the block design because many people hate it, including me. So you can just go in here. Sorry, apparently I forgot to set here the IP paths. Repository, yes. So I will actually show you all the steps which you have to do. IPs, no, not this IP folder. Identification, IPs, here we go. Select, and then you see here already there's 4 IP cores in there, and when I do now, here, yes, user IPs, then I've UART, and with Vitus HLS IPs, I have the Axie master example, which I just created and packaged. And this one I actually can double click on, for those who have not seen that functionality yet. So I have example component name, Axie, HLS 1, whatever. And then I can define even the widths and everything. And I will create it. The nice thing in here, it will create it once. And I do not need to use the block design for this. And I can just write normal sources up to it. And it will create that file, and then I can work with it as a normal AXI file. So I have here now in my block sources, I have it in here, but I can also use it, and I can put here a wrapper around and use it as a design source. Alternatively, we create block design, as you have learned in the course. You will just load in here your AXI HLS here. AXI master example, you will create this, and then you see already it looks different. So it looks like an HLS IP core. Now I say I want to have a RISC-V processor connected, whatever, right? And then I have these blocks in there. And I see here, I have a slave AXI control. Interesting. So I can literally connect my AXI control to whatever RISC-V AXI I would configure. And then this is accessible, and I can control it, for example. Or you can connect it to Ethernet or whatever tasks you have come up with. And then from then on, you know the design flow. It's literally the same design flow as before. To be honest, I find this very geniusly simple. There's a few clicks is knowing where to look, but then the flow is quite straightforward. Yes. Any specific questions? I will not go too much into the HLS syntax in writing of that because I'm not expert in it, and I do not require you to write something huge in it.
What's the pre-production meaning there?
This? So basically, that's a good question where it is defined. It's probably because it's not yet tested, and I have defined it somewhere in the default settings.
Tag, probably.
It's a default setting probably when I package it or so.
It doesn't have a meaning other than just a...
No,
Okay.
it's just a tag which you have somewhere. What was it? Probably something which you.
It's most probably.
Yeah, it's something which is done in your workflow. Yeah, yeah, exactly. Don't know exactly what it is. I've not worked too much with it, and I also have not worked with the new with this new design yet much. But it's something which will be quite interesting for us also from a research point of view. Because, just to summarize from the lecture, HLS is being used for anything algorithmic. If that's signal processing, so FFTs, whatever, to visual processing, waveform stuff, transcoder, whatever, encryption, all these kind of things is algorithmic. Everything which is a system control, an SD-RAM control, a sensor control, all these kind of things you usually do on a VHDL level because it's controlling on a very low level where bits matter.
If we are talking about SoC, then the chip itself should control the.
Not necessarily.
Not necessarily.
It depends.
But,
It really depends. Just for the use case, it's HLS for algorithmic if you do not need maximum performance. If you need maximum performance, VHDL, or of course if you're good enough in coding, and you have like the experience, then
sine waves.
yes.
Writing
If you know how to optimize your code towards throughput or latency or whatever, then you're going to be better than HLS, simply put. Because it's a generic tool which will have an overhead because it will use standard solutions. If it sees a for loop, it will implement always the same logic for it.
What C libraries are supported? Like standard.
That I cannot tell you from the top of my head.
But the standard.
I suppose so, at least for your test bench testing and those kind of things.
The OOP because it's C++.
That I don't know. I've not tested it in a long time. It's not a real C++. I just look in I would really go through the document. If you want to code anything, look in the documentation of support. I have not done much, but for the project scope which I expect from you, I also wouldn't expect you to need any libraries. Like I expect you to do some equation solving or whatever kind of thing, something algorithmic. Run through an image if you really want to. Something big would be if you run through an image and do something on an image, but that's already quite big.
Yeah. Oh my God. There's like a lot of drivers already pre-written.
Yes, especially for the system on chip stuff, there's a lot of drivers written.
Yes, a lot.
Yeah, but of course, everything which you would do on a normal FPGA is not existent because you have custom any memory or whatever.
Yes.
I think that's clear.